Welcome back to the channel. Today we're going to be covering some performance aspects. Now this channel has gone back almost 5 years, and during that time I've created over 1,500 videos. Now this channel is not monetized. I didn't collect a single dime off of any of those videos. And during that time, this channel has affected the way the performance industry has been moving forward. It is pointing out the facts, getting into the small details, identifying the issues and problems that we have within a performance industry. That's what has been done through YouTube channels across the United States or from around the world. It is technology that is allowing us to ask questions, debunk some things, and even create some drama. That drama also leads to more investigation, to things that might be affecting the performance industry. So today we have two topics that we're going to discuss. And if you haven't been part of this channel, obviously we dive deep into the mechanics, the actual engineering behind the American V8 performance engines. Now, many of these technologies are shared in every combustible engine, diesel engine, gasoline engine, and even into turbos and jet engines, as we're hearing the F-35s fly over today. Now, approximately 5 years ago, one of the first videos talked about the piston pin offset and how certain engines can benefit from actually flipping the pistons around from bank to bank in order to achieve more additional horsepower. Realizing that every modification that we do to all these engines, the engines still rotate in the same direction. So one modification to one bank is going to negatively affect the opposite, and it normally balances itself out. A few months later, we also identified an issue with hydraulic flat tappets within the performance industry. Since the late 1990s into the 2000s, the quality of camshafts, the engineering, has not kept up with the change within the mechanical devices. Whether that's parts being made overseas or parts that are not being held to the same parameters within their manufacturing. YouTube channels across the United States and around the world have identified what they believe is what's causing the issue. Some are saying it's the lifters. Some are saying it's the quality of the oils. Some are saying it's the camshafts themselves. Well, that's through the metallurgy or the actual surface material. Now, over the last 5 years, with all the discussions and all the opinions being added in from multiple YouTube content creators, have we really identified exactly what the issue is? Now, in this video, between camshaft location and piston sizes and piston rings, those are the two topics that we're going to discuss here today. And hopefully you guys can see I'm using a little bit more of a fine tip marker, so it might not be as obvious to some of you. But the top picture is just two cam lobes, a cross-sectional drawing of the lifter and a cam lobe. Now this is going to be for both hydraulic flat tappets, solid flat tappets, and hydraulic and solid roller type systems. Understanding what the original engineers back in the 1930s and 40s, what they were trying to achieve with the capable products that they could make back then within the industry, will allow you to understand why some of the modern modifications aren't necessarily working, because it wasn't originally designed to use it. Well, modern technology within roller systems relieve one issue, they cause another. So we're going to be getting into camshaft position. We're going to focus on the three main manufacturers. Obviously, Ford, Chevy, and Chrysler. They all engineered their engines a little bit different. The Chrysler had a lot more in common with the Fords. The Chevys were kind of standalone. And then all these sub-companies underneath them, whether they're General Motors or American Motors, they shared and swapped different ideas. And it was always the competitive nature to top their competitor, trying to make a better design. Ford had attempted to do that with multiple different engine combinations. They would use one, try to modify it to work with the same stock that they have available, from the FEs to the 385 series to the Windsors to the Clevelands, Ford attempted to do multiple different things. Now, depending on what engineer within the Ford Corporation they used, they came up with a different design, but they normally didn't look at the entire picture. Chevrolet spent a little bit more time identifying in the 1950s what was the most efficient and cheapest manufacturing process to create the first generation Chevy. And throughout history, over 50 years, the small block Chevy was known to be a powerhouse. It was something reliable, used in muscle cars to everyday transport vehicles to heavy equipment, even 5-ton trucks. Same thing goes with Chrysler. Ford, within the engineering aspects, they tried to keep the engine size paired with the chassis that it was going to be used in. Now, you can argue and have the arguments between your small block and big block comparisons. Realize within the history, those times changed. And as cubic inches grew, it was because of other factors, whether it's competition in NASCAR, restrictions in different racing syndicates, cylinder head design, engine compartment restrictions. It was designed to fit within a chassis. So what's the first thing that an automobile manufacturer designs? All right? If you look throughout history, it was normally the outside of the car. The engine compartments are very large, so they could fit any engine combination that they wanted to in them. Whether it's a very large straight 8 to a smaller straight 4. Individuals that have been mechanics, you can appreciate the older cars. You can literally climb into the engine compartment to work or fiddle around with something if you had to modify something on the engine. It was fairly simple. We've gone the opposite direction with the performance industry to the point where the engine compartment, if not every square inch is filled with something, you're not among the norm. So today we're going to go back and compare the original engineering plans from both Chrysler, Ford, and Chevy within the hydraulic flat tappet type design. I just seen a video this morning where somebody was disassembling an engine. So the engine was built by another shop. The customer wasn't satisfied with it. It had wiped out a couple cams before they finally got it to work. And now they've decided something's still not right, so they brought it back in. Upon disassembly, we noticed the cam positioning. The lobes are directly underneath the center of the bores. Now, if you know about hydraulic flat tappets, they need to spin within the bore to have an even wear surface. And in order to do that, the cam lobe itself has to be manipulated to where one side of the lobe is actually taller than the other side, to where that has a progressive contact patch on the side of the lifter, causing friction to actually turn the lifter. As the lobe continues or advances, more contact is made across the face of the lifter in order to move the valve train in its proper direction. The bottom circle, or the non-pressurized lift point within the motion of the cam, the lifter actually makes contact entirely across the cam lobe. The base circle is flat. There is no canting to it. Now that variable going from the base circle to its max peak within a lobe, the cam lifter has to rotate before it reaches its maximum peak lift. That transition is called the aggressiveness of the cam profile. The faster the cam leaves from its base circle to its maximum lift, that entire distance is your aggression. And within that aggression, your cam or lifter lobe spin also has to be taken into consideration because you don't want it coming to a stop at maximum lift when it's underneath the maximum of pressure. So if you look at a worn camshaft, you'll typically see, without being able to have to put in a cam doctor and actually measure it, you'll actually see the travel and the contact patch of the lobe between the lifter. It will typically start on one side of the lobe at its peak and even out within the ramp. The sooner that contact patch comes to the middle will tell you how aggressive the ramp profile is. Without having to have all the extensive equipment to measure all this, you can tell just by looking at a used camshaft. Now, what we've noticed, and some channels have already identified, is that the crown of the actual lifters aren't being machined the exact same way that they were back in the 1930s through the 1980s. The American manufacturing used a different way of grinding the face of the lifters themselves to create the crown. Overseas, they're machining it differently. Okay, so that is introducing some problems into the flat tappet arena. Cams themselves are also being designed differently. They're being machined differently. So one of the channels that I've had disputes with is Spire Race Engine, or excuse me, not Spire. Yeah, it is Spire. Out of the North Carolina area. I can't remember what the channel's name is now. He's a small business owner that creates camshafts, and he is using the technique of where the cam core is actually held into a lathe and the grinding wheel rides on a guide. So the grinding wheel, the actual stone itself, has a lot to do with the consistency from lobe to lobe to lobe. So for you old-time machinists out there, do your stones, when you're doing a valve job, when you are setting your tapered stones into the cylinder head itself, and you are touching down and grinding the different angles into your valve seats to create the contact patch, or on the valves themselves, you realize the stone wears out. Even if there is a lubricant, water, or an oil mix traveling over the stone to keep it cool, as it makes contact, the flakes or the individual sand beads of these stones, they come apart, creating a radius within the stone itself. Now, depending on how often the actual stone is changed out or refreshed, right? You old-time machinists, you understand this. You have to redress your stones as soon as they start to wear out. So your consistency from one valve pocket to the next is going to change because the stone wears out. Unless you're dressing the stone between each individual valve pocket or valve seat, they're never going to be exactly the same. How many out there are doing that? Same thing goes with cam grinders. As the cam core is spinning in the lathe and they bring in the guided stone, from every single lobe they will change from the front or to the back. The first lobe that they're grinding to the last lobe. Are they dressing that grinding wheel between each individual lobe? There's going to be an inconsistency from front to back. Now, modern day technologies have realized that they're not using stones anymore to grind the valve seats. They're using a carbide. The carbides are much stronger and can last a lot longer. They're more durable when they're cutting even harder materials than previously used. They're more consistent from each individual valve pocket or cylinder. When it comes to piston bore diameters, even the finish on the wall is going to be dictated of which one is done first. So you see the honing machines that are being calculated and controlled by computers. They're measuring how much pressure is being applied to the stones, how many cycles it's gone up and down, and approximately what the wall finish should be. But as that machine picks up and goes into the next cylinder, the stones are no longer the same. They're actually a finer grit. So unless you're changing your honing stones every single bore, you're going to have a different finish for every cylinder that you do, and succeeding to every single engine that you do afterwards with those exact same stones. This is machine shop performance. Now, individuals can pull out their micrometers and measure everything, but you will notice with the machine shops, performance machine shops, they cost a lot more because they are replacing the stones or the equipment used to do the machining more consistently. Or they're taking the time to reface the stones, or to make sure that the carbides are fresh more continuously, that they have a consistent result throughout all of their engine builds. A typical backwoods or a garage machinist, they don't have access to that technology. Or if they do purchase the equipment, the main equipment, they are not changing out the tooling often enough to compete with major race engine shops. Very large and expensive machinist shops, say like a NASCAR shop or a NHRA type shop that's, pounding out pieces of performance parts, they cost a lot more because they use a brand new set of either stones or carbides every single process within the build. Cost adds up fairly quickly. Now this morning I seen a video with a big block Chevy that had been returned, complaining about some of the camshaft issues, and the owner believed that the cam was walking around. That could be one of the reasons why the premature cam failures leading up to the return. Now, upon inspection, viewing it as the engine is sitting apart, just the short block, viewing down from the top through the lifter bores, you could see that the cam lobes were directly centered underneath the bore. Right? The sides of the cam lobe itself fit inside of the cam bores. They didn't extend wide enough to where it could make contact with the very edge of a flat tappet cam. After removing the cam and doctoring it, finding out all of the different lobe profiles and so on and so forth, matching it to the engine, which the big block Chevy uses a 904 lifter, the cam lobes were only 875 wide. Okay, hopefully you're following along. So the cam lobe was more narrow than the actual lifter. Upon inspection, the lifters had, after a short run time, the lifters themselves had a friction mark that was elongated, and it didn't reach across the entire face of the cam lift or the lobe lifter. What is the actual problem? Where is the issue? Is it the lifter? Is it the cam? Is it the machining process? Or is it the position of the cam as the engine is running? That's the detail that we wish to cover the most in this video. Between Ford, Chevy, and Chrysler, they all used a different way of retaining the camshaft within its proper zero position, putting and placing the cam lobes directly underneath the lifter bores. Now, all of them have some kind of a aftermarket device for when lobes start to increase, or when cams become more of that race-oriented design. Ford and Chrysler both use a front retaining plate, keeping the camshaft from moving any far forward. The Chevy variations the cam button, which normally is located in front of the cam, in front of the timing sprocket, it is the timing cover that can manipulate where and how far the cam is pushed forward or back. The Ford has actual casting at the rear of the cam that restricts the cam from moving back. Okay, so the bearing surface is larger, but then in the rear portion, the casting of the block is actually smaller, keeping the cam from moving any farther backwards. They use the cam restrictor plate on the front between the timing chain or timing sprocket to keep the cam somewhat centrally located. There's obviously a small variable in there to take in consideration for expansion and contraction, keeping the cam within a zone. So it keeps the lobe underneath the lifter. Chrysler also uses the front retaining plate, but the rear cam can actually be manipulated in its position by how far the rear frost plug is being driven in behind the cam. In the area between the frost plug and the back of the camshaft, there's actually a cavity that is directly fed by oil pressure, with one of the main oil galleries located under the rear of the camshaft itself. It causes a hydraulic cushion. So a mechanical device holds the cam in from the front, and it's actually the oil that absorbs the cam movement forward or backwards under acceleration or deceleration. The Ford's mechanical within the cast in the block. It is mechanical devices. The Ford also uses a front bearing between the camshaft and the front retainer plate. So each manufacturer designs something a little bit different. With a small block Chevy, the front timing cover, once a cam button is installed, can be manipulated with simply just either hammering or pulling out the timing cover to allow more movement within the travel of the camshaft forward and back. Ford restricts it from moving forward and also from moving backwards. Chrysler has a mechanical device from it moving forward and a hydraulic restriction from moving backwards. Now, another thing that causes the camshaft to move forward or backwards, outside of the hydraulic flat tappet lobe design, is also the distributor drive gear and the rotation. The contact point between the distributor gear and the camshaft gear also forces the cam forward. Now, a machinist is going to typically treat every single engine, whether it's a Chevy, Ford, or Chrysler, to the exact same experience that they have. If you take your engine just to your local machine shop, they're going to treat the cam exactly the same way unless they specialize on a certain brand. If you're building a Chrysler, you want to turn to individuals that do nothing but work with Chrysler engines. If you're working with Ford, you want to turn to individuals that specifically work with Fords and Chevy, and so on and so forth. A high-performance shop, an individual with a lot of experience, is going to be able to be handed any engine and identify exactly what needs to be done to achieve the maximum amount of performance. They're also going to know the difference in the things needed to be identified, whether the customer wants to use hydraulic tappets or rollers. The cam manufacturers only take two things into consideration. If it's a flat tappet or a roller, that's all they take into consideration. They don't take into consideration that, say, maybe even a small block Chevy guy has opted to bore out the lifter boards and use the Chrysler's 904 lifter within their performance build. Your Chevy cams are not listed to say this one is being intended to use the 8 or a 9 lifter bore. The big block Chevy that we got in was designed for the original 396s, which used a smaller lifter. The camshaft that was ordered was destined for the smaller, earlier variation of the big block Chevy. Realizing just a couple years later, they also went to the 904 lifter bore. Excuse me. It is extremely hot and humid out, guys. My throat's dry from talking. In today's performance industry, experience counts for something. And in today's performance industry, depending on your specific engine build, you need to turn to professionals that have specialized within that engine family. Even within a Ford family, if you have somebody that specializes in FEs and you're building an FE, turn to them, to their advice. If you go to a Ford shop and they just say, yeah, we're a Ford dealer or Ford machine shop, ask them more precisely, what Ford engine do they know the best? If your combination that you're building is not the top of the list, keep looking for a machine shop. Now, there are some YouTube creators out there that specialize in Ford builds. And they will concentrate more on the performance combinations. Within the Ford industry. More of that car or muscle car chassis combinations within the FEs, so on and so forth. They will attempt to build a Cleveland, a Windsor, or an FE in the exact same machine shop. And they will practice the exact same measurements and checking processes with all three engines. But all three engines had different engineers. Even though they're a Ford power plant, they had different engineers that made them. And those engineers had a completely different mindset in training and education when they built those engines. So a machine shop might say, oh, I'm just going in to install some cam bearings. Okay. What was the original designer intending to do? What tolerances did they incorporate into the design? That's what comes with experience. It's not the machines. So for you garage guys out there, even your YouTube creators that, okay, I'm finally starting to collect some money, I'm going to buy a piece of equipment so I can start pounding out camshafts to sell and make a little bit of a profit. You have nowhere near the experience of the original engineers. You're going to modify things, what is common and norm within the performance industry. But the original engineers know more and knew more than you ever will. So even after owning the engine shop, I didn't have one lead machinist. All of our machinists specialized in one single engine family, knowing the tolerances expected around the original design. So if we were building a Ford Cleveland, it was the Ford Cleveland machinist specialist that worked on it. If you were building a Hemi, there was specific Hemi guys that did all the machining on the work. Because every single engine build needs a specialist to maximize performance and longevity. Folks, it's a combination. Our camshaft failures that would have been occurring for the last 30 years in every single engine combination is because everybody has their thought process. What they've been taught is the norm, and it's not specific to the combination. Now moving on to the next topic. This won't take very long, a couple minutes. The same thing goes with piston diameter and bore clearance. These Chevy that lasted for 50 years. The specs are all over and available for anybody to read and apply to their building application. Modern day performance engines are closing that gap to much smaller tolerances And they're also using piston rings that are much thinner and under much less tension. Well, these modifications might be showing additional horsepower in a dyno. They're also consuming a lot more oil within a combustion chamber, and they're also causing parts like pistons and cylinder walls and piston rings to fail. So even modern technology might be a move in the right direction for something like horsepower creation. It's trading off longevity. And if you go back to the original designs and the engineers that built Ford, Chevys, or Chryslers of the 1930s, 40s, and 50s, what did they get out of their engine combinations? Longevity. That was the original design of those engines. If they lasted longer and consumed less oil. Modern technology hasn't necessarily solved the problem. They've actually added to it for the trade-off of higher numbers. Okay, you can get 60,000 miles out of your engine that creates 20 more horsepower. For 20 less horsepower and older engine designs, you can have that same engine that'll last 500,000 miles. It's your choice whether or not you want to follow along with the norm or go back to the original engineers. Have a good one.